Hi everyone, my name is Emma Schaefer, and today I'm going to be presenting on oxygen heme transport. So hemoglobin is a heterotrimer because it has four subunits that are not all the same. There are two alpha and two beta monomers. It has four subunits of myoglobin, which each have a heme prosthetic group. Each heme has an iron binding site, so hemoglobin is able to bind to four oxygen molecules, one at each heme site. Hemoglobin has two different conformational states. It is in the R state if it has any bound oxygen, and it is in the T state if no oxygen is bound. These two states are shown in the image where the T state is deoxyhemoglobin and the R state is oxyhemoglobin. So the binding of oxygen molecules is successive and cooperative. So binding to the T state is harder than binding to the R state of hemoglobin. This is because there are slight conformational changes that occur at each monomer, which make it easier for the next oxygen molecule to bind. Therefore, in the body, hemoglobin is mostly in the R state. If the T state does gain a bound oxygen, it makes a conformational change to the R state. So in order to effectively transport inhaled oxygen to tissues, the pH of sites where oxygen is bound must be different from the pH where oxygen is released. At physiological pH, about 0.6 protons will be released by hemoglobin every time it has an oxygen molecule bind to it. If the pH is increased, hemoglobin binds more to oxygen. This is called the Bohr effect, and it is illustrated in the graph to the right. So in this graph, the x-axis shows the partial pressure of oxygen, which is equivalent to the concentration of oxygen since it's a gas. And then the y-axis is its fractional saturation, and this is just the fraction of full oxygen sites on hemoglobin. So oxygen is bound in the lungs where the pH is 7.4. At this higher pH, oxygen is bound tighter. It is also bound due to the high concentration of oxygen in the lungs. Oxygen is transported through the blood where the pH is 7.6. The higher pH ensures that oxygen stays bound to the heme, despite the fact that there is a relatively low oxygen concentration compared to the lungs. So the binding capacity of oxygen to heme in the capillaries is slightly higher than the binding capacity of oxygen to heme in the lungs. And this helps transport it to the necessary tissues without releasing it too early. Oxygen is then transported to and released into the tissues, which have a lower pH of 7.2. At this lower pH, oxygen wants to be released. Additionally, the concentration of oxygen at the tissues will be lower, which also increases the release of the oxygen in this area. Another important aspect in this pathway is the creation of carbon dioxide by cellular respiration in the tissues. The carbon dioxide that is created by these tissues is diffused from the tissues and forms bicarbonate and Bohr protons when it reacts with water. And this is shown in the equation at the bottom left. Usually this process occurs slowly, but red blood cells have the enzyme carbonic anhydrase, which accelerates this reaction. So when this occurs in the capillaries at relatively low oxygen concentration, the Bohr protons will react with hemoglobin to form its T state, which causes it to release its bound oxygen molecule. When this occurs in the lungs at high oxygen concentration, the Bohr protons are released when hemoglobin takes up oxygen and forms its R state. These Bohr protons are then react with the previously formed bicarbonate to create carbon dioxide in the lungs. This creates a process where oxygen can be transported to the tissues that need it, and carbon dioxide can be returned from the respirating tissues to the lungs And this is shown in the diagram on the bottom right.